Today, we will learn about the role of central processing unit in computer system. We will also learn about the major components of the central processing unit and purpose of each component in detail. We will discuss types of buses found in computers and describe the purpose of each type of bus. Also, we will learn about what are the differences between RAM and ROM and describe their use. Hello everyone, I am Priyanka Bharti and today we will learn about Central Processing Unit in detail. This diagram shows human brain. As we all know, our brain is vital organ of our body system. It controls activities and processes, integrates and coordinates the information it receives from different body organs. At the same time, it also makes decisions and sends instructions to perform tasks accordingly. This is the diagram of Central Processing Unit. Similarly, Central Processing Unit is the brain of the computer. It controls and monitors all the processes that takes place inside the microcontroller unit. Now, let's start with two types of memory used in our computers, that is RAM and ROM. RAM stands for Random Access Memory, or it is also called read or write memory, whereas ROM stands for read-only memory. RAM is used by the computer for temporary storage of programs and data. Here, data is lost when the computer is turned off. For this reason, RAM is called volatile memory. ROM is used for permanent storage of programs and data. Here, data is not lost when the computer is turned off. ROM contains programs and information essential to operation of the computer. The information in ROM is permanent. That means it cannot be changed by the user and is not lost when the power is turned off. Therefore, it is called non-volatile memory. Now come to the internal organization of computers. It has three parts: central processing unit, memory, and input-output devices. All components of the computer system are under the control of the central processing unit. The function of the CPU is to execute or process information stored in memory. Peripheral devices such as input-output devices allow the central processing unit to communicate with humans or other computer systems. Memory is used to store programs and data. The CPU is connected to memory and input-output devices through a strips of wires called bus. The bus carries information from place to place inside a computer, just as a street bus carries people from place to place. There are three types of buses in every computer. These are address bus, data bus, and control bus. The control buses are used to provide read or write signals to the device to indicate if the CPU is asking for information or sending it information. Control buses are used by the CPU to direct other devices. For a device to be recognized by the CPU, it must be assigned an address. The address assigned to a given device must be unique. No two devices are allowed to have the same address. Here, device is memory or input-output. The CPU puts the address on the address bus and the decoding circuitry finds the device. Here, address must be in the form of binary. The address bus is used by the CPU to locate a device or a memory location. Then the CPU uses data bus either to get data from that device or to send data to it. That means data buses are used to send information back and forth between the CPU and other devices. Of the three buses, address bus and data bus determine the capability of a given CPU. Let's learn address and data bus in detail. This diagram shows internal organization of computers. Let us first learn data bus. As we know, data lines are used to carry information in and out of a CPU. The more data lines available, the better the CPU. That means to increase the performance of the CPU, we should increase the data lines. More data lines or data buses means a more expensive our CPU and computers. If we use more data buses, then cost of CPU will increase automatically. The grouping of data lines is called data bus. The average size of data buses in CPU is between 8 and 64. For example, Apple II has 8-bit data bus. Supercomputers like Cray has 64-bit data bus. Data buses are bidirectional. That means it can be used as either to receive or to send data by the CPU. Also, the processing power of a computer depends on the size of its buses. That is, 8-bit bus can send out 1 byte at a time, whereas 16-bit bus can send out 2 bytes at a time. Now come to address bus. Address bus is used by the CPU to locate a device or a memory location. If we increase the number of address buses, then more number of devices can be addressed. In other words, the CPU can communicate with more number of locations if more number of address buses are there. Formula to find the number of locations is equal to 2 to the power x. Here x is number of address lines regardless of the size of the data bus. For example, 2 to the power 16 is equal to 65,536. Here 16 is the address lines of the CPU and 65,536, that is 64 kilobytes, is the addressable memory. Each location can have a maximum of 1 byte of data. In this case, total accessible memory is 64 kilobytes. The address bus is unidirectional bus, which means that the CPU uses the address bus only to send out address. Hence, we summarize all. We can say that the total number of memory locations addressable by a given CPU is always equal to 2 to the power x, where x is the number of address bits regardless of the size of the data bus. Now let's learn CPU and its relation to RAM and ROM. CPU is used to process the information. For this, data must be stored in RAM or ROM. The function of ROM is to provide information. The information stored in ROM is fixed and permanent. For example, programs to display information on the video monitor, programs for testing and finding the total amount of RAM installed on the system. RAM is also used to store information The information stored in RAM is not permanent and can change with time. For example, various versions of the operating system, application packages like word processing or text calculation packages, etc. Here, these programs are loaded into RAM to be processed by the CPU because the CPU cannot get the information directly from the disks since the disk is too slow. This is the main reason due to which RAM and ROM are called primary memory and disks are called secondary memory. This figure shows the detailed diagram of the internal organization of the computer. As we know, program is stored in memory. This provides instructions to the CPU to perform an action. Function of the CPU is to fetch the instruction from memory and execute them. CPU has many resources for fetch and execute, that is, registers, ALU, program counter, instruction decoder. Let us learn about all of them with their functions. First one is registers. There are few registers, namely register A, register B, register C, register D, and instruction register. Registers are used by the CPU to store information temporarily. Depending on the size of the CPU, register can be 8-bit, 16-bit, 32-bit, or 64-bit. Here, increase in the number of registers and their size, the better will be the CPU. This is the reason due to which cost of CPU will also increase. This is the only drawback or disadvantages. Now come to arithmetic and logic unit. It is used to perform arithmetic functions such as addition, subtraction, multiplication, and division, and logic functions such as and, or, and not. Now come to program counter. The function of the program counter is to point to the address of the next instruction to be executed. How this execution takes place? The contents of the program counter are placed on the address bus to find and fetch the desired instruction. Fourth one is instruction decoder. The function of the instruction decoder is to interpret the instruction fetched into the CPU. It is like a dictionary we all have. Like dictionary, it also stores the meaning of each instruction. It will decide what should be done by the CPU after receiving instructions, or we can say what steps the CPU should take upon receiving a given instruction. As in dictionary, more number of pages means more words it defines. Similarly, CPU can understand more instructions, and also more instructions require more transistors to design. Let us understand how computer works internally. See the following example. These are the steps and code to perform the operation. Let us suppose the program to perform the actions are stored in memory locations which will start at 1400 H and end at 1406. These are the contents for each memory location. Now let us learn how will the CPU perform the actions to run the program. As we know, program counter has a value between 0000 and FFFFH. We first set the value of program counter to 1400H, which indicates the execution of the address of the first instruction code. As soon as the address of the first instruction has been coded in the program counter, the CPU is ready to execute, means CPU will start the execution process. Second step is the CPU puts 1400H on the address bus and sends it out. The memory circuitry finds the location while the CPU activates the read signal, indicating to memory that it wants the byte at location 1400H. This causes the contents of the memory location 1400H, which is B0, to be put on the data bus and brought into the CPU. Third step is the CPU decodes the instruction B0 with the help of its instruction decoder dictionary. When it finds the definition for that instruction, it knows it must bring into register A of the CPU the byte in the next memory location. Therefore, it commands its controller circuitry to do exactly that. When it brings in value 21H from memory location 1401, it makes sure that the doors of all registers are closed except register A. Therefore, when value 21H comes into the CPU, it will go directly into register A. After completing one instruction, the program counter points to the address of the next instruction to be executed, which in this case is 1402H. Address 1402 is sent out on the address bus to fetch the next instruction. Step 4 is from memory location 1402H, it fetches code 04H. After decoding, the CPU knows that it must add to the contents of register A the byte sitting at the next address 1403. After it brings the value into the CPU, it provides the contents of register A along with this value to the ALU, that is Arithmetic Logic Unit, to perform the addition. It then takes the result of the addition from the ALU's output and puts it in register A. Meanwhile, the program counter becomes 1404, the address of the next instruction. Fifth step is address 1404H is put on the address bus and the code is fetched into the CPU, which is decoded and then executed. This code is again adding a value to register A. The program counter is now updated to 1406H. Final step is the contents of address 1406 are fetched in and executed. This halt instruction tells the CPU to stop incrementing the program counter and asking for the next instruction. In the absence of the halt, the CPU would continue updating the program counter and fetching instruction. Let us suppose that address 1403H contained value 04 instead of 42H. How would the CPU distinguish between data 04 to be added and code 04? Here, code 04 means to move the next value into register A. Therefore, the next value will not be decoded by the CPU. Despite its value, it only moves the contents of the following memory location into register A.